Okay, I want to look at this one right here. So we're talking about the first 2 seconds, making an approximate rate function, and then estimating the number of feet the car has moved in those 2 seconds. So for the first 2 seconds, we're talking about from here to here. In the first 2 seconds, so this is the rate of change function for this remote control car, and for the first 2 seconds we'd be going from 0 to 2 seconds. And our goal is to, say, find the distance traveled by, or the number of feet that the car is from its starting point at 2 seconds, or the change in number of feet traveled in those 2 seconds. Okay, so the first, question 4 was, which one of the choices below show an approximate rate of change function for the first 2 seconds based on the left approach? So let's first figure out which ones of these, first of all, which ones of these show an approximate function? Which ones of these show an approximate rate of change function? Does A show an approximate rate of change function? No, it shows rectangles. It's not showing a function. So A and D are not showing a function. So the other 4 here to the right. So now we want the left approach. So let's narrow it down here. So which of these 4 show a left-hand approach? B and E. Right, people are saying B and E. Do you agree with that? Yeah, B and E are the 2 that show a left approach. And so now what's the difference between B and E?
B is
yeah, so B would be going to 2.5. It shows an extra step there, an extra approximate from 2 to 2.5. But that wouldn't be included in the time from 0 to 2. So the answer here is E, because we only want for the first 2 seconds, or 0 to 2 seconds for the interval. Okay, and then if we wanted to approximate, so we're looking at, this is the approximate rate function that's been specified, using the left approach and showing it for the first 2 seconds. So estimate the number of feet the car has moved in the first 2 seconds using this approach. Choose the closest answer. And so remember we said that the total change okay. So total change given the rate function is going to be the sum of the many bits of change. So it's going to be sum of, I think we call that function f. But we're using particular values of f, we'll call those k's. And then I is going to go from how many I values do we have? How many k values do we have? 4. So we're going to do our first approximate rate times delta x plus the second approximate rate times delta x, etc. and add those 4 together. Yeah, I think it's 6. I think the correct answer is something close to 6. Okay? And so then where do these rates come from? So this rate is actually what? F of 0. It's the function value at the left side, which is the left side is 0. And then this one would be f at what? 0.5. And then this would be f of 1, and then f of 1.5. So those were those rates. Those constant rates are coming from the actual rate of change at the left side of each interval. Okay, so what do these other two graphs over here have to do with it? They're not showing an approximate rate function, but they are showing something related. What they're showing is they're showing that, so if you think about each of these k times delta x, we see that, for instance, right here, this width right there is our delta x. And this is the second rectangle, so f of 0.5 is whatever this y value is right here, but that y value is represented by f of 0.5 is represented by this distance right here on the graph, right? This distance right here is that k2, or f of 0.5. It's like a 3. Okay? And then this distance, delta x, is this width right here. So because we're in the rectangular coordinate system, this k delta x, this bit of change, rate of change times delta x in the rectangular coordinate system, then also becomes the area of a rectangle. Width times height. So delta x is like the width of this rectangle, and then the rate of change then is the y value, so it's this height, h. And so in a geometric sense with the graph, these bits of change can be also thought of as areas of rectangles. Area 1 plus area 2 plus area 3 plus area 4. And maybe in your Calc 1 class, that was the more emphasized approach. Okay, but it's really it's more of a superficial thing that just comes about simply because we're in rectangular coordinates, and that's just kind of what happens. But then that kind of our whole calculus world got latched onto this idea of area, and then that became the meaning for integral. Okay, but it's really a superficial kind of incidental meaning because we set up the axis that way. Okay, so is this the same one? Yeah. So these areas then, so A and E are kind of corresponding graphs. E showing the approximate rate function, A showing the resulting rectangles that would be the areas. The areas of those rectangles would also be these bits of change in our quantity. And in this case, number of feet that the car has moved. Okay, so is this going to be an overestimate or an underestimate? What do you think? She said underestimate. So this amount of feet that the car has moved in the first 2 seconds, using the left approach, she wants under. Agree with that?
We spend more time under the real function than above it.
Yeah. So yeah, the rate is below for these 3, and then only for this last one is it above. And so then, how does that play out over here?
We're going to underestimate the approximate distance traveled.
Right. So let's talk about what we would get then if we wanted to make our approximate better and better and better. What would it mean for the area of these rectangles? What would it mean for the sum of the area of these rectangles if we did better better approximation of this total change. Yeah, so more rectangles. What would the implication be? Okay, so here's a kind of a similar picture. I got this function. Is this using a left side approach or right side approach?
Left. Right.
So if you look at a particular rectangle, is the height of that rectangle coming from the value of the function at the left side or the right side?
Left side.
Left side. Okay, or you could just look at this little slide right here and see that it's set to left. Okay. All right, but anyway, so hopefully you're only looking at the picture. So what would happen then to make a better approximate total change? We're going to use more more slices, or a smaller delta x.
More K's.
More k's, right? So here's that. And so what happens in the area analogy, the sum of the rectangles? What happens as we use more and more k's and a smaller and smaller delta x? What happens to the sum of the rectangles? More exact to what? The sum of the rectangles then approaches, what does it approach? Yeah, so it's the area defined by the curve. That's the most I can do. So you see now the error is very low. The tops of those rectangles are doing a really, really good job of matching the curve. And so adding up the areas of the rectangles is becoming closer and closer to, okay, fine. Closer and closer to an actual area. So that blue area there, with more and more, this is left, this is right now. With more and more rectangles, the sum of the rectangles approaches the area that blue area there. So then our meaning for integral in this sense, so that integral can represent area defined by the curve. It doesn't make sense. So just to summarize, we said that the sum of many bits of change becomes the actual true amount of change as delta x goes to 0. Approximate total change. Becomes exact amount of change. But now if we think of this as a sum of rectangle areas, as that delta x gets very, very small, as it goes to 0, and those rectangles get very thin, the integral then, in this kind of thinking this way, the integral is area between the curve and the x-axis. From A to B. So the next part of the course is going to be focusing on this way of looking at integral, looking at it as area. Okay, and so then there's more like looking at it as geometry, rather than looking at it through the lens of rate of change. So looking through the lens of rate of change is more meaningful, and that was that's the original purpose. But because we're in rectangular coordinate systems, rectangular coordinate system, we can look at it through the lens of area. And that's what we're going to do. Okay, any questions on that? So let's look at some examples here. So the function y equals 5x minus x squared. So in terms of these, we're going to have a lot of these functions, these graphs. It's going to be a combination of you knowing how to sketch these graphs without a calculator and sometimes using your graphing calculator to help you. But a lot of the basic ones, you should be able to make a sketch of the graphs without your graphing calculator. Okay, for instance, this one. This one we could factor as x times 5 minus x, and how does that help us sketch the graph? What do we know then? If y equals x times 5 minus x.
We know we've got a translation to the right.
Okay.
And we know that we've got parabola. We know that it's
Okay.
upside down.
X squared is parabola.
It's upside down.
Y upside down, how do you know that?
Sine.
Okay, so minus x squared, we'll say opens down. Okay. So can we get, that's some general things. Can we get some specifics?
We can find our intercepts.
Yeah, right. So
We can solve it.
you don't need to solve anything to get the intercepts. What are the intercepts?
X equals
0 and 5.
Yeah, so if x equals 0, y would be 0, right? And if x equals 5, what would y be? 0, right? So those are your roots, okay? So it would be 0 and 5.
We can find.
And it's going to open downward, right? It's going to open downward, so we're ready to make a sketch, okay? So if it goes through these 2 points and opens downward, then somewhere on here we got the vertex between those two.
We could also find our max.
Uh-huh, good. You could find your max using calculus. You could change the form of it to find the max. But this is for our purposes. This is good for getting started. Okay, so say we want to find the area.
But it also, we can intuit that it's halfway.
Yes.
The midpoint.
Uh-huh. Midpoint between the roots. It would be at 2.5. You could plug 2.5 in and get the max as the y value. Yep. So we could find the area enclosed by y equals 5x minus x squared and the x-axis. Okay, so make sure when they're describing the region, read very carefully what are the things defining the region. Okay, so sometimes students that put the graphs up, and then they won't really read exactly what's defining the region. So you got to read that really carefully. And so here I'm saying, enclosed by, what's the region enclosed by this curve and the x-axis? So does everyone see what that would be?
0 to 5.
What's that?
0 to 5.
That's implied. Is it from 0 to 5? Or just says enclosed by y equals 5x minus x squared and the x-axis?
That's the only part enclosed between the graph.
Right, okay, so it's going to be this here. Okay, that part there. Okay, so here's how we're going to do that. So thinking about these rectangles, what we're going to do is we're going to sketch a typical strip. Okay, so and that's like a rectangle, but we'll call it a strip. So a typical strip will be, say, like what I said, be like our rectangle, okay? So that red thing is a typical strip. And so we want to get the area of that. So the area is just going to be width times height, because it's the area of a rectangle. So what is the width of this typical strip? Width first. So I'll draw it again here. What's the width of that? X. Is it X?
Or x2 minus x1. There you go. Delta x.
Yeah, so we're thinking it's relatively small, so it's going to be a change in X. X, this would be X. It's not, so that X is, the X coordinate is how far you are from the Y-axis, or how far to the right you are on the graph. Now, so for the width of that strip, it's a little change in X, so it's delta X. Okay? And what is the height of this strip?
5x minus.
So the height of this strip literally is the Y value. It's the Y value of that curve. But since we're doing it as delta X, we need that Y to be in terms of X. So what is the Y value in terms of X? What is that Y in terms of X?
F of x of k.
No.
5x minus x squared.
Yeah, so that's what Y is. Y is 5x minus x squared. That's what Andre said before. So the area of our typical strip is going to be width times height. Width is, I'll change it around, height times width. So the height is 5x minus x squared, and the width is delta x. So what am I going to do? I want to get this area that I want. I want to sum up all those strips, starting where and ending where. I want to sum up the strips. So that's just a typical strip. I could have chosen it here, or here, or here, or here. All right, so where's the first strip? It's 0, right? The first strip is at x equals 0. So the total area is the sum. How do we write sum? How are we going to sum up these strips? Yep. We could write it as sigma, but if we wanted exactly, like if the strips are really super thin, yeah, so the integral is the sum starting at x equals 0, ending at 5. And what are we doing? We're summing up the strips, the areas of the strips, the typical strips. So they are 5x minus x squared dx. This would be for finite width delta x, and so then we use the integral to say we're summing up them if they're really super, super thin. And so that's why the delta x then is dx. So this is the area of a really thin strip. And we're going to add up all of them starting at 0, ending at 5. Okay, and so we could get a number. This will give us a value. And that value will be the area of the shaded region. And it's easy, right? Don't even need to do it. Okay, so what if we looked at instead? What if we any questions on that one? So now I'm going to start with an integral. And ask you, what would that represent? So now I'm going to say 0 to 8, 5x minus x squared dx. What would that represent? What's that? The area outside.
Because 1 to 8 and 8 is not part of the area.
Okay. Other.
The net area.
What does that mean, net area?
So like the area above the curve that's bounded by the x and the y, between y equals 5x minus x squared and the x-axis.
Yeah.
Minus what's below the x-axis from 5 to 8. So the net of that.
Okay.
It wouldn't tell us much.
What's that?
I don't think it would tell us much.
It wouldn't tell you much.
The sum of the strips. This is basically what it said. The sum of the strips from 0 to 8.
Okay, the sum of the strips. The strip is an object. The sum of, what about the strips?
The strips, the area of one strip is equivalent to 5x minus x squared times dx.
Okay.
So the sum goes from 8 to 0 to 8.
Okay, and so, yeah, what's going on here? So let's look at a good picture of the graph here.
Why would we care to know what's going on from 5 to 8?
Why would we care to know what's going on from 5 to 8? Well, we're integrating from 0 to 8. So from 5 to 8 is part of the integral, right? One more time. There we go. So I've got a skewed version of this. So what's it going to mean from 0 to 8? So let's revert back to rate of change, right? So if this was a rate of change function, this would be a rate of change function. What would it represent in terms of total change? What would be happening here as x increases from 0 to 8 for this rate of change function? Somebody knew. How about, yeah, Brock?
It would be increasing 5
Okay.
and start decreasing.
And it'll start decreasing. Okay, so your quantity would be increasing from 0 to 5 because the rate is positive, and then the quantity would decrease from 5 to 8 because the rate of change is negative. And what do you predict for this, for the overall results? Looking at this. What would you predict for the amount of change?
To be negative.
He wants negative. Why?
Just estimating looks like the rate of change is significantly more negative from 5 to 8 than from 0 to 5.
Awesome. Notice he didn't talk about area. He talks about the rate of change. He said, look, the rate of change is significantly, from 5 to 8, is significantly more negative than the positive that it was from 0 to 5. Okay? So we've got this increase, and then we have a decrease in the amount of quantity because of the rate, and he thinks maybe that decrease was more than the increase, just by looking at the rate of change. So if we were to do it, I'll just do it on the solver here.
This is just like the race car, huh?
Uh-huh, something like that. So let's just put it in and see if we get negative or positive. So 5x minus x squared. Negative, so he was right, negative 10.7. Or negative 10 and 2/3. Would be the overall change. So how can we make sense of negative 10 and 2/3 in the context, in the lens of area now? We're looking at areas. Can't have negative area, so what is going on here?
Do you remember the car problem? Well, when it goes backward, it's negative.
Right.
Like, but it's not really like, not moving or it's increasing in rate of, according to its rate of change. It's just like going backwards.
Okay, so I understand that. I'm wondering about area. So how can we make sense of this in terms of area? If it's negative 10 and 2/3. Yeah.
The area got smaller by a certain amount.
Okay, so, but the area ended up, how can we have negative area? In the end, we got a negative value.
So the area between 0 and 5 is smaller than the area between 5 and 6.
Okay, so 0 to 5 would be this area here. And then 0 to 8 would be so does the integral give total area?
No.
No. Did it add these two together and give you the area? No, we got a negative value.
You necessarily subtract this fundamental theorem.
Yeah, so it represents, what does this represent? It represents a difference of areas. And that's what Brandon was talking about, net area. By net area, we mean anytime the area is above the x-axis, it will have a positive effect on the total integral. Anytime the area is going down from the x-axis, because the function is negative, those areas get subtracted out of the total, and a negative contribution to the integral.
And so does that only apply to the x-axis, or does it apply to any axis that, any line that you choose?
No, x-axis. Because think of it as rate of change, that's where the zero rate of change is, x equals 0. So this is positive rate of change, so we get a positive contribution to the change, negative rate of change. So then we get a negative contribution to the total change. So in the lens of areas, anytime the area is above, you're going to get a positive, that area will be added into contributing to the value of the integral. Anytime the area is below, you're going to be subtracting that out. So if you wanted to, so can you write an expression that would calculate the total area? Can you write an expression that would calculate the total area? Call this say A1 and this A2. Could you write an expression that would calculate the total area? Do it. You should be able to do that.
slap an absolute value on this? Should we just flip the sign?
It depends what you're thinking. You're just going to do this?
Yeah, that looks bad.
That doesn't look bad. Is it right? No, is it right? What's the answer? So if you did that, the absolute value of the integral, what would you get?
No, I wanted to split and then on the second.
Because we tried mine. He's one right.
If you're splitting it, then why would you want to do that? The whole point of using the absolute value is to not have to split it.
Right.
Okay? If you're going to split it, then just adjust it so that you'll add the total areas.
Yeah.
Okay. So if you want to use absolute value, will this work?
What does it actually mean? How does that affect our subtractions?
Yeah, that's what I'm asking you. What is this going to do? What is this going to do?
So it's going to do.
Is it right? What does this say to do?
So just take the integral.
It says take the integral and make it positive. Take the integral and make it positive. Is that right? What's the integral? What was the integral? We found it. What's the value? Negative 10.667. So then you can make it positive. It's going to be 10.667. Is that the sum of those two areas?
I don't think so.
No. Well, there's more.
So we should split it.
You can split it, or you can correctly use absolute value. So your idea was good. Your execution was bad. So how are you going to use absolute value?
We put an integer.
Okay? Will that work?
Jeez. I'm trying to do it, man.
So you want to do this. What about that? Will that get the sum of the areas?
Because now it's going to be 5x plus this.
Now it's going to be 5x plus x squared. It's going to change the function to 5x plus x squared. No, that's not what that does at all. It takes the function value, and if it's positive, it keeps it positive. If the function value is negative, it makes it positive.
Good.
Oh, I see. Oh, because I'm not graphing. This is what I meant. So there's the function of the absolute value, and if I take the integral of that, I'm going to get 52.3333. Sorry. Yeah, because it'll take the integral of this, and that'll add this area plus this one, which is what we had before, just flipped up.
Is this a rule?
Uh,
Like, can we consistently apply this when we have functions that go above or below? Let's say a periodic function.
you answer that question.
I think yes.
So this always, wherever the function is negative, it gives you the positive version of it. And then, yeah, so then you would get total area. But so that's fine, but we should also understand how we could do it as two separate integrals.
Yeah.
So from 0 to 5. And then what would we need to do from 5 to 8 if we were going to split it up?
Subtract.
So it's kind of like the absolute value is kind of cheating a little bit, right? It's like, so what would you do?
Well, we know the second one's negative,
Right?
so we have to subtract.
Yeah, or add the, so subtract or add the opposite, yeah. So, yeah, you can subtract is perfectly fine. I'm just going to emphasize it by saying add the opposite. That would get total area, right? Because 0 to 5 we know is positive. From 5 to 8, we get that negative for the opposite of that area, so then we have to take the opposite of it to make it positive. Okay, questions on this discussion? Yeah, so normally if you're asked to find total area, normally you would write it as separate integrals. And whenever that, for whatever region just has a function below the x-axis, you're going to take the opposite of that integral to make it a positive area that you're adding. But know that if you just take the whole thing from 0 to 8, you're not getting a total area, you're getting a difference of areas, just like with net change, or just like total change is going to be all your, whenever the rate is positive, it's going to add to your total change. Whenever the rate is negative, it's going to subtract from that total amount of change. And so that's analogous to what happens with area. When you're below, you end up subtracting that area. That's what that integral does.
Is the modulus of the function about the same as what we have down there?
What's that?
Is that modulus of 5x minus x squared the same as equivalent to the area we're getting between 5, from 0 to 5, and from 5 to 8?
I didn't understand your question. Did you say mod?
Is this area the same as what we have out there?
Which area? Is the
Are you talking about the sum of the areas?
The sum of the two different.
The sum of the areas is this expression right here.
Yeah. Is that the same as what we have out there?
Yep, it's this. It's the same as,
But that's
The-
not the black cross hatches. The second half is reflected above the X.
Well, yeah. They're not just them, right?
I'm still not following.
You still not following me.
Yeah, your question. What's not the same?
That out there is down here.
There's
Really?
several things up there, and there's several things down here.
Okay. It's down. I mean, this. Is it the same as this? No, because this gave us maybe 10.6, and that gave us.
No, I added the opposite of. If you just take the integral from 0 to 8, it will subtract off at any area where the curve is below. So by just looking at from 5 to 8 where it's below and taking the opposite of it, now it's going to add that area plus that area. A1 plus A2 is written this way. So this A1 plus A2 is there's your A1. The opposite of the integral from 5 to 8 is the area A2. 10.6 is this.
What's from 0 to 5?
0 to 8 is negative 10.666. Negative 10 and 2/3. Because it's a difference of areas. It's this one, this minus this area. Which would be like the total change. The total change if this is the rate function. You have some amount of positive change and then a greater amount of negative change. So you get the total change is negative. So this is A2, A1 minus A2. Negative 10 and 2/3. If you want A1 plus A2, then you have to take the opposite of the integral from 5 to 8 and make that part positive and then add it to A1. If that's what we're doing there, down there. Is it better? Okay, so let's look at another example. Y equals 1/2 x cubed. X plus y equals 6. See if you can sketch this without your graphing calculator and the y-axis. Can you sketch that without your calculator? Just for practice. So consider the region enclosed by. I'm sorry?
Is that going to get seeded or squatted?
What's it? 1/2 x cubed?
The half. Is it going to make the y?
Well, is it going to affect the y values or the x values?
Like the x values?
It's going to check that. It's going to change the x values.
No, y values. Excuse me.
What's it going to do to the y values?
It's going to make them half as large.
That's how you think about what it'll do to the graph then. Think about it at a point at a time. What will it do to the points? Whatever it does to the points is what it does to the curve. That curve is points.
So it brings in closer to
What's that? How are y values? What's the y value of a point? What's the y value of a point?
bring it down.
Half the side, right? Half the side. That answer your question?
Yeah. Just having trouble.
We're just sketching though, so just
Yeah, I just want to get good at this because I struggle with this.
yeah, sure. But so you're taking half of every y value that you had before. So think of graphs as a bunch of points. Each point is going to have a y value that's 1/2 of what it was before.
So the result will be, so rather than this will just be squatted.
Sorry. So let's see how you did. Okay, so what are we talking about? What region are we talking about there? So here's your y equals 1/2 x cubed. Here's your x plus y equals 6. And the y-axis, so which one is it talking about? This here. Right? No, Patrick.
I want to buzz it.
Here, this.
No, you're fine.
Where?
To the left.
Left. This?
Yeah, there you go.
Okay. This. Okay, so what are we going to do? We're going to do our typical slice. Our typical slice is going to look like this. Or what do I call it? Strip. Sorry, typical strip. Area equals height times width. So what's the height of that strip? What's the height of that strip? How would we conceive the height of that strip? So this up here, is it a y value or an x value? Y value, so we'll call it, say, y2. And this here, y value or x value? Another y value, y1. So in terms of y2 and y1, what is the height of that strip in terms of y2 and y1? Right, it's y2 minus y1. You see that? It's the height to the top of the strip, which is y2, minus the height to the bottom of the strip. I'll give you that change in. It's like a change in height, right? So it's final minus initial. W is delta x. So now we need the whole thing in terms of x. Y2 equals, in terms of x, 1/2 x cubed. All right? What y2 is 1/2 x cubed. We'll go with it. And then y1 is 6 minus x. Is it right?
y2 is 6 minus x.
He wants y2 to be 6 minus x.
Whichever one's above.
Okay? Which one is above, Andre?
The linear function.
So you think this is right or wrong?
That's
It's wrong. Y2 is defined by this, what you said, the linear function. That's the 6 minus x. And then y1 is defined by our curve, 1/2 x cubed. So there's the area of a typical strip. It's going to be the y2, 6 minus x, minus 1/2 x cubed, all times delta x. And so that's true. This expression is true for every strip, starting where and ending where. So then the total area,
7 from 0 and ending with
The intersection.
intersection. Yeah, that is the intersection.
So the function is equal.
so from 0 to what is this right here? And we're going to add up all the strips, and each strip is going to be 6 minus x minus 1/2 x cubed dx. So we could call that, so like that's like dA. That whole thing is like dA. It's like a little strip of area. We want all of those. We're going to sum up all of those, starting at 0, ending at
The midpoint. Or the edge of the point which is
yeah. So how are we going to find out where they intersect? All right, what are you going to set equal to each other?
The two functions. Half x cubed equals 6 minus x.
So we want to. So you don't set the functions equal to each other. You set their y values equal to each other. You set the y's equal to each other. So it's going to be 1/2 equals. So x cubed equals, get rid of that.
If you just factor in x, you can guess.
What's that?
If you just factor in x, you can guess.
Okay, tell me.
So, okay, so now x cubed equals negative 2x plus 12. And then x cubed plus 2x is 12. And then x times x squared plus 2 is 12. So then, what can I square and add 2 multiplied by 2 to 12?
Yeah, so this would be, so
This is convenient.
this is appropriate to, like, now you use your graphic calculator to find the intersection point.
But also, if you draw it well, you can use your paper. Like if you have consistent scales.
As an estimates.
As an estimate to confirm.
Yeah.
What you're asking.
But what it turns out to be is x just turns out to be 4. So 2. Because 2 cubed is 8, divided by 2 is 4, 6 minus 2 is 4. So it's 2, 4. But so this is, you could, graphic calculator is fine to find that. Okay, so we're going to integrate from 0 to 2. Any questions on that? So now what I want you to do is, I want you just to set up the expression. So these, lots of these integrals just are really easy. They're just polynomials after all the hard stuff we did. So I'm not going to take the time to do all that. In your homework you will. but it's better for us to set up more examples in class. So this first thing for the sheet here, I want you to now find the area between the same two curves on the x-axis. So the region formed by that curve and the x-axis. All you're going to do is set up the integral. Set up the expression.
I don't want to go there, just like real quick. Where does this like get really hard?
Does it get really hard?
Yeah.
I don't know. I guess we'll find out. In the homework. Maybe it won't.
Never does. It always does.
Okay, so now the challenge is you should have. So why is this one different? What does it require? Yeah, you can't do it with one integral, right? You should come. Your conclusion should have been that you had to use two integrals to get this area, right? So how can we write it in one integral? Can we write it as one integral?
From 0 to 6, new box from 0 to 6, then you have half x cubed plus in parentheses you can put 6 minus x.
That's not good.
Right. Oh,
But the boundaries are going to apply to what they're doing.
I see.
So the reason you can't write it as one integral is because
Oh, yeah.
your typical strip over here is different than your typical strip over here, right? And you all did the typical strip, right? You wrote typical strip for the first, and you wrote it out, right? And then you did it for the second one, right? You all wrote that out, right? So how can we write it as one integral? That means we would need one typical strip that would take care of the whole region. Any ideas?
Right in the middle. Touching the intersection point.
Well then, just so only that one?
Well, the boundaries are described by two different functions.
Okay.
You can't have one integral.
So is there a way that one strip could do the whole thing? Yeah, you're doing it with your pencil.
Horizontal.
Yeah, horizontal strip. If you did a horizontal strip, you could. There's only one that you need, right? And then our first one would be down here at the x-axis, and the last one would be at this point. And so if we added typical strips that were horizontal, we could do it in one, because that typical strip comprises the whole, is the same for the whole region from bottom to top. Do you see it? All right, so area of a typical strip. Equals?
Well, it's the same, right? Width times height.
Width times height. So, sure. Okay, and what's the height now? Let's start with the height. Delta y. And then what's the width?
x2 minus x1.
Okay, good. So now to define this length, it's going to be x2 minus x1. And so what is x? But we need those in terms of y. What is x2 in terms of y? What is x2 in terms of y?
Y equals 6 minus x.
It's our line, right? So it's going to be 6 minus x?
6 minus x.
No. We need what x is. We need what x is. X equals
6 minus y.
6 minus y. X doesn't equal 6 minus x. We need that x value, and so x is 6 minus y. What is x1?
Cube root of 2y.
Yep, so we got to solve this for x.
I already proved this.
You can do it in your head. Good for you. So x is cube root of 2y. So that's a typical strip, and that's the same one for the whole region. The first, where's the first strip at? So the total area is? Minus the cube root of 2y
dy.
dy. Where's the first typical strip? These are going to be y values. So the first one is here at y equals 0. And where's the last strip? Yeah, remember we said this point was 2, 4.
Yeah, right.
So the last strip is at y equals. I don't know why I wrote that. So if you were to do that integral, you would get the same number as the one that you did, which was the sum of two other integrals, right? Because you're calculating the same thing, you're still calculating the area. So the value of that integral should be the same as the sum of the two that you wrote.
Wow. This is nuts.
So then how do you know which to do? So now we have a choice, right? So do you write the integral in terms of x or in terms of y? And it depends on the problem. And then many problems can be done both ways. So we wrote it both ways. Writing it with respect to x requires the sum of two integrals. In this case, writing it as one integral would require doing it with respect to y.
So which one should we, or does it not matter at all?
Whichever one you can solve.
It would depend on what's being asked for in the question. If you're just being asked for the total area as a number, then whatever. So you can do whatever you want, because they're going to give you the same value. But if it says write it as one integral, then you have to decide, is x going to give you as 1 or y? Or they might, so it's possible that both could give you that as one integral. In this particular example, x requires 2, y requires 1. Okay, so let's try one more. Oh, shoot. Let's just practice sketching the region, and we'll talk about what the solution would look like without doing the whole thing. But so consider R enclosed by x equals 1 minus y squared and x equals 2y squared. So could you sketch these without your graphing calculator? In fact, if you try to use your graphing calculator, it messes students up. And so you need to know what those look like. X equals 1 minus y squared. Well, it's a parabola, and it's gonna, but now x equals 1 minus y squared. So it's gonna open down, but now down is in the negative x direction.
So the right. Left.
It's gonna open to the left, right? And when y is 0, x is 1.
Oh.
And then it's gonna open to the left.
Yeah, if you put it in our calculator, we'll get the top half.
Yeah, if you solve for y, it'll break it. You'll have a plus or minus. There's two functions that you'd have to put in.
So could we just say plus or minus root negative?
No, say x equals 1 minus y squared.
Got it.
All right, and then x equals 2y squared. That's going to open to the right because it's positive. So the region is enclosed by x equals 1 minus y squared and x equals 2y squared. So do you see the region? Is it this? Is that what the region is? Okay, so notice it doesn't say anything about an axis, right? So here it doesn't say an x-axis or y-axis. So it's truly the only thing defining this region are those two curves. So you need all of this. Okay, so if we did it with respect to x, how many integrals would we need? 1, 2, 3. How many integrals do we need if we did it with respect to x? Yeah, we could do it in 2. Is that the way to go? So all we need to do is get the area. Is x the way to go? What about with respect to y? Just one integral, right? One integral. And a similar lesson. So your typical strip would be this here.
That's 1 minus y squared.
And it would be x2
So what? 1 minus 3 y squared?
So going to be more convenient to do it in x or y? Why? Because not only is it only one integral, but then you're going to have the width of that thing. It's going to be x2 minus x1. And look, you already have those. You don't have to do any solving, right? The functions are given as x as a function of y. So it will be, what is x2? What's the value of x2 in terms of y? Is it the 1 minus y squared or the 2y squared? x2.
Whichever one's on top, so 1 minus y squared.
That's x2. You can do 1 minus y squared minus x1, which is 2y squared dy from what to what?
From 0 to the right-hand root.
From 0 to the right-hand root.
Whatever that
Agree? Okay, but our strips look like this. These are our strips.
Oh. Intersections.
Yeah, so the first strip, the first horizontal strip is this y value here. Say y sub a. And then your strips are up like this, right? And then your last strip is that? Up here, so I call it y sub b.
What was the question?
You're going to integrate from what to what? Yeah, so when you integrate, so you're summing up all the typical strips from the first to the last. So the first typical strip is at this y value, whatever that is. And so you're going to need to solve for that y value right there. And then the last typical strip is going to be at this y value. Yeah, so if you're doing it in terms of y, then your bounds are going to be y bounds. And it makes sense because your typical strips are horizontal. So the first one's at the bottom, and then the last one is at the top. Definitely want to do it in terms, this one in terms of y. It's much more convenient. Because you don't have to rearrange your things. These are all set up in terms of x's. And then you can just do it, just one integral does the trick.
Could you just show us the boundaries for the x approach?
X would be from what to what? So you're thinking now your typical strips are this way. So where's your first strip? 0. First one's at 0 until, well, so until that x value, then you need a new integral.
So we're using this one and then the other one.
And then, so you need, so the first integral, you would go from 0 to the x value of the intersection. The second integral would be the x value of the intersection to x equals 1.
Is this going to be 0 anyway?
What's that?
Is this going to be 0 anyway because it's reflected about the y or x.
We're finding the area. Finding the area. Total area. So it will not be there.
Finding y a and y b would be just the same, just setting equal to each other and solving go on.
Finding the y values, right, when the x's are the same,
So
right?
it just ends up being like a plus or minus something.
By symmetry, it'd be the same. This would be the opposite of each other, yeah. Okay, so there is web work for Monday. Web work for Monday. And we'll go over the exams on Monday. But sometime I'll post. I will post the results before then if you want to see results, or if you want to see how many you got right on just the multiple choice before you leave.
Can I check mine?
Yeah. Solids of revolution. So we're going to take these areas that you worked on and we're going to revolve them around an axis or some kind of line, and it gives us a solid. And we're going to find the volume of the solid. Okay? So let's just get the general idea here. So what did we start with? We said, at first we said we're going to sum up what? Bits of change. And then that will equal, when we sum up a bunch of bits of change, we get? Total change. Trying to establish a pattern here. In this last homework, what do? We summed up what? Areas, right? Areas of rectangles. And that gave us the total area of whatever region those rectangles swept out, right? Okay, so now we're going to be summing up volumes of some different things, all right, depending on the way. And those volumes are going to, these individual volumes are going to come by taking the rectangle, just the rectangle, the typical rectangle, and rotating it around the axis. And we're going to get some kind of typical volume, and we're going to sum up all those volumes, and we're going to get total volume. So this is the pattern for all these problems, okay? German S means sum up. We're going to sum up a typical version of something, and then when we do that starting at one value all the way to another value, we get this area, this region, or this volume. Okay, so let's look at something real simple here. So let's do, say, y equals let's just go real simple here. Y equals x squared, and we'll look at then the line x equals 2. And the x-axis. And so we start with this region here. So y equals x squared, x equals 2, and the x-axis. Okay, and then we're going to revolve around the x-axis. So it's going to be this region in here. And we're going to revolve that thing around the x-axis. Can you imagine what volume you would get when you did that? Can you imagine what that will look like? Lots of times food is helpful to describe these things. Okay, so yeah, it's going to look like a Hershey's Kiss. So were you thinking that? So let me try to draw it here. So it's going to look like this. Something like that. So how are we going to do this? Well, we're going to do the same way we did before. We'll start with that area that we're rotating, and we're going to do the typical rectangle, first of all. Okay? And we're going to figure out what we get when we revolve that typical rectangle around the x-axis. That will be the element that will be the typical element of volume. Do you see? So when we rotate that typical, that rectangle, that red rectangle, when we rotate that around the x-axis, what will that shape be?
Or a circle with edges.
Yeah.
Think food. Okay? It's like a pancake, okay? It's going to be like a pancake, but standing up on its end. Okay? So when we rotate that thing around the x-axis, we're going to get if your pictures aren't great at first, keep working on it, okay? So I have a little bit of practice with this, so I can make some decent pictures. Okay? So this is our typical pancake. So your book and web work will call these discs, okay? Discs, but pancakes are a lot more fun, okay? So whenever you see discs and pancakes, exactly the same thing. Okay, so that would be, this is going to be like, you know, here. Okay, so there's our typical pancake, and so then what are we going to do? We're going to sum up the volume of all the pancakes starting at x equals 0 until x equals 2. And when we sum up all those volumes of those pancakes, we'll get the total volume of the Hershey's Kiss. Make sense? So what is our volume of our typical pancake? So what shape is a pancake or a disc? Cylinder, right? So that's going to be, so it's going to be pi r squared times height, right? So let's start with the height. What is the height of this pancake? It's a little change in, this is the height right here. What is that?
Delta.
Yeah, they're saying delta x, and that's right. That's our height. Okay, what is r? What is the radius of the pancake? So the radius is going to be like this right here.
Shall we take it as well?
What's that?
1.
It's not 1. They change, right? The radius changes. This is just typical pancake. So the height of the rectangle. So the radius is the height of our original rectangle. Need y2 minus y1?
Can we get y2 minus 0?
Yeah, you just need y, right? It's just y. It's just y, because you're going to 0. So you don't. You could do y2 minus y1, but you'd be subtracting 0 because you're right. So this is the y coordinate of the top of the curve. So our radius is just y. It's going to be y squared and then pi. But we know we're going to be integrating with respect to x, so we need that y in terms of x. What is it? What is y? Y is x squared. So it's going to be x squared squared. So we got the volume, we got it. So these problems start getting more long and involved. It helps to do your setup work, like put it in a box, okay? So it separates out the setup work. Okay, so every one of these pancakes has a volume of pi x to the 4th delta x. These right here. Right, so that volume of that there is our pi x to the 4th delta x. And we're going to add up all those volumes of all those pancakes from where to where? 0 to 2. Where the first pancake will be at 0, x equals 0. And the last one will be at x equals 2. So we're going to do integral 0 to 2 of pi x to the 4th dx. Volume of the kiss. Questions? So super easy integral. Questions on that? Does that make sense? Okay, so let's do a variation on this problem. See something else here. Can I erase? So the first possible volume would be volumes of pancakes.